Martijn and I will go over this evidence synthesis R package. So I will go first. I plan to spend 20 minutes to explain the rationale for this evidence synthesis package and the modeling procedure. So before we get into the detail, I want to kind of offer the greater background about the why we are doing this, and then why we should use different approach other than meta-analysis. So as you know, we are collaborating through this Odyssey research community. The setup is that we have the data from different different sites. The data are, let me see, yeah, the data are stored at the local server. So behind the firewall, we cannot share. Typically, we cannot share patient-level data freely due to the privacy and the regulatory reasons. So this distributed research network is fairly general. Beyond Odyssey, there are many other distributed research networks that are in states. In United States, there are PICONETs funded by Obamacare. There are lots of health systems having their data stored locally. And another feature of this distributed research network is that we typically the data are standardized in certain common data model. So such as OMOP common data model from Odyssey, and also PICONET common data model. So with this standardization, there's a hope that we can perform the same data analysis on the same data format across different sites to help with the reproducibility of the generated clinical evidence. So the operation-wise, typically there is a study lead. So for example, I work at UPenn. We have data converted in common data model at UPenn. So we do have I want to initiate a project. So I serve as a study lead where I have the access of the patient-level data. And then locally, I can develop some analytical code. So those codes can be fairly complicated, such as high-dimensional propensity score model to control for the effect of confounders. And then we distributed those codes to different sites, asking different data partners to run those codes locally, and then send their results to the lead site. So this is a typical divide and conquer approach. And so there are lots of examples in this following this implementation strategy. So this is a paper published 6 years ago evaluating the risk, the adverse event associated with a certain treatment. So basically, as you can see in this forest plot, some data partner contributed some analysis results. As you can see here with confidence intervals, and then you just run a meta-analysis to combine those results together. So this is basically the divide and conquer approach, and use meta-analysis, random effects meta-analysis to combine the results. So that's the current approach. And in this approach, what has been shared when we conduct this analysis? So first of all, we know we cannot share patient-level data. And typically what has been done is that within each data site, we run a large-scale propensity score model, and then to control for confounders, and then we run an outcome model to estimate the causal effect. The causal effect is that the causal effect is typically analyzed by fitting stratified time to event analysis model, such as a stratified Cox model, or you can fit a conditional Poisson regression model. For those models, they typically cannot be reconstructed by sharing as simple as 2x2 tables. If you have a binary outcome that can be shared by running 2x2 tables, but for those Poisson regression and Cox regression, cannot be handled by sharing 2x2 tables. And what has been done in practice is to just share the point estimate of the causal effect, and then also share the standard error. And through the meta-analysis approach, you will do inverse variance weighting to combine them together. But the issue here is that if you have in settings such as epidemiological study or pharmacovigilance study, when we study relatively rare outcomes, the underlying normality assumption made by the meta-analysis procedure may not be valid. So this is a real data example. So as you can see, if you use a normality assumption, you will get the hazard ratio of with this confidence interval of 0.27 to 3.78 for this hazard ratio. On the other hand, if you don't impose any shape assumption, you will have a different confidence interval. This is because when you have a rare outcome, the likelihood function is not following the quadratic approximation. So there is a deviation from this normality approximation, normality assumption for this distribution of the likelihood function. So that is the issue when you the number of events are relatively low. So another example is that if you have even more rare outcomes, such as this setting for the targeted treatment, you don't have any events in this targeted treatment group, and in this situation, the likelihood function is actually monotonic. So this likelihood function is actually monotonic. Then obviously this quadratic approximation or normal approximation cannot be applied. So this actually raises the serious concern about the standard meta-analysis approach applied to this type of study, especially when the number of events is relatively small. So in the evidence synthesis package, what we are proposing people to use instead of meta-analysis is to share the likelihood function rather than the simple point estimate and standard error, because the point estimate and standard error largely rely on the normal approximation, and that normal approximation really is heavily dependent on how many events you have. So often the time, regardless how big the sample size is, if you have a few number of events, this normality approximation can be fairly off. Like this one has some difference, as you can see, from this difference in this confidence interval with or without normality assumption. And in this example, there's this function, likelihood function is monotonic, heavily deviated from this normality the normal distribution. So the solution we are advocating is actually very simple, which is called likelihood profiling. So this paper was published last year at the statistical method and in medical research. So the key idea is that we just communicate the shape of the likelihood function rather than communicating the point estimate and the standard error. So let me just go over the idea. So in the commonly used situation, where we have a single causal parameter of interest, so we can first run a propensity score model to adjust for all the confounders. And the second step is actually to fit a simple model, which is say a stratified Cox model with only one variable, which is a treatment indicator. So this model only has one parameter. So eventually what we want to communicate is the log likelihood function, the value of log likelihood function over a grid of possible values for, say, log hazard ratio. So we have previously tried a number of options. So we can use normal approximation, which is the strategy we advocated not to use because that requires a larger sample size. We also tried this skewed normal approximation. We also tried this custom approximation. At the end of the day, we find that the best approach, based on our extensive simulated studies, we find that the grid-based approach actually gives us the best performance. It seems that the grid-based approach is the most robust approach. So what we need to do is that we just simply construct a grid from all the possible values. For example, the log 0.1 as a hazard ratio, log hazard ratio, to log 10, which is also the log hazard ratio. So basically, hazard ratio range from 0.1 to 10. This covers a wide range of possible values for hazard ratio. And then for each grid point of this over this range, we share the value of this log partial likelihood function. So using this strategy is not going to be impacted by the rare event or zero counts, because it's going to basically communicating the log likelihood function. We don't need any approximation of the likelihood function. So on the other hand, when we talk about this data privacy, so this log likelihood function is unlikely to contain the patient privacy information. So in most of the cases, we can just communicate this log likelihood function. So just to make this algorithm a bit smarter, instead of having equally spaced grid points over the range, so the current version of this evidence synthesis package has this adaptive grid option. So basically, we can just refine the number of points, the grid points, when this likelihood function has more curvature, has more changes. So, and then for the functions that are relatively locally linear, then we can just assign less grid points. So this will be more economical in terms of a number of grid points to be shared. So just to share the idea, so how it operates is that the leaders data sites initiate code to share this to share a particular log likelihood function, and then for each participating site, they will construct their local likelihood function, and then share those grid point value, and then send those values to the study lead. Then study lead will aggregate those likelihood function and construct this aggregated likelihood function, and all the inference will be based on this aggregated likelihood function. So that's how it operates. I'm going to pause here and see if there's any question. Okay, otherwise, let's keep going. So current version of evidence synthesis package implements two different models. The model we just talked about is a so-called the fixed effect model, meaning that the different sites. Sorry, this is there's auto in advance. So the fixed effect model basically is a model that, assuming that different data partners are estimating the same causal effect, and then by pulling them together using aggregated likelihood function, we are going to estimate this the common causal effect across all the data partners. So in reality, a lot of times that the causal effect may be different across different data sites due to reasons such as unmeasured confounders, unmeasured effect modifiers. So in this case, we can use a random effects model, and through this Bayesian network, Bayesian meta-analysis approach. So this is implemented using the BEAST MCMC engine developed by Mark. So now I'm going to get a little bit into the detail of this this approach. So the standard meta-analysis approach is assuming that the beta I, which is a causal effect at the I sites, follows a normal distribution with a mean of mu, and the variance is tau square. So this mu is the average treatment effect, by aggregating the site-specific causal effect beta j into a single scalar summary, and the tau square is between site heterogeneity in this estimated causal effect. So the Bayesian meta-analysis approach is recommended in our setting because we want to account for the uncertainty associated with this mu and this tau square parameter, because typically in many of our distributed network studies, we only have a limited number of sites. So the estimated tau square also is associated, comes with some uncertainty. So using this full Bayesian approach, we can account for the uncertainty associated with the estimated mu and uncertainty associated with the tau square. So this is a example of the posterior distribution for the mu and the tau parameter. So in the literature of meta-analysis, it's well understood that the estimate of the heterogeneity parameter tau could be ill-behaved if we only have a small number of sites. So often the case that if the number of sites is relatively small, we don't have sufficient power to estimate this tau square. So we could be mistakenly assuming the model is a fixed effect model when the model is truly a random effect model. So using this full Bayesian approach, we will be able to truthfully reflect the uncertainty associated with this the tau parameter. So now we talk about how to estimate the causal effect in the context of fixed effect model and the random effects model. So just to make some connection with the previous lecture, when we talk about the use of negative control to adjust for the systematic error. So in principle, seems that we have two approach to aggregate the information across different sites. The first strategy is that you can get some local causal effect estimator, and then you can apply the negative control, and then you can do some calibration locally, and then for the calibrated effect, then you can use some type of meta-analysis or likelihood profiling to combine them together. That's one strategy. The second strategy is that for this causal effect of interest, we can use the likelihood profiling to combine them together into a one likelihood summary. And then for each of the negative control, we are going to use this evidence synthesis approach to summarize. And then we can do the calibration on the summary level, summary estimate of interest. So these two approaches at the first sight seems to be similar. And however, so there's a good reason that we recommend the use of the second approach. So the first reason is that if you it's actually visualized in this diagram. So typically you can specify a fixed list of negative control outcomes, and that list of negative outcomes should be shared across different sites just for the consistency. And for some sites that you may only have very few or even zero outcome for either treatment group or the control group, then you don't have any estimate. So for those sites where you don't have any estimate, then it's difficult to conduct the local calibration, right? So on the other hand, if we use likelihood profiling, so we can still get the likelihood function for each site, regardless of whether you have 0 outcome or not. So you will have still get a summary of this with respect to this negative control outcome. So this, using the second strategy, the summary estimate of negative outcome should be easier to work with, and then you don't have to job any particular site. That's one reason. Another reason is that the second approach focused on this calibration using the summary estimate of interest can also truthfully reflect the systematic error related to a particular data set. So imagine, I think this is the scenario that typically got ignored, in the sense that if we, the traditional meta-analysis is, the standard error actually contains two pieces of information. One is the standard error due to the finite sample size for a given data set. The second piece of the standard error is reflecting the impact of the systematic error due to the confounding effect. So using the second approach is we'll be able to disentangle the impact of the final sample size from the impact of a systematic error. So that's the reason we the second approach should be applied. We should focus on calibration using the summary estimate of interest. So that's the workflow. So do we have any questions?
There are a couple of questions. Yong, there are a couple of questions in the chat.
Okay.
When you get a chance, let's have a chance to look through those, and we can do them parallel with other work as well.
Do we have a paper on calibration in the Bayesian context? Martijn, do you have an answer on this Bayesian this calibration on Bayesian context?
Yeah, the answer is no. So we don't currently have a paper specifically combining our new form of meta-analysis with calibration. Although we have applied it in various studies, but we don't have a paper specifically on that topic.
Yeah, the second question from Scott is yeah, Scott, maybe you could elaborate the question if you the weighting issue.
Sure. I was just wondering if when a function is generated with very few person days or very few events, if it would be weighted differently. But Mark answered that it is reflected in the curvature of the likelihood function. So,
yep. And the next question is from Harold Lehman about the issue of cell size, and I'm asking for small counts. So we are communicating the likelihood function is actually rather than the tables. So we don't have a direct issue of the cell size. So I know for many consortia there are some constraints that the number of we can only report if the number is smaller than 10, we can only report that the number in particular cell is smaller than 10. We cannot give the actual number. But on the other hand, if we report the likelihood function being monotonic, is actually suggesting that the cell is is 0, or so that could be a study, something we can study later. Maybe some privacy related concerns, right? So monotonic typically is directly associated with 0 cell in any particular group. So regarding the potential privacy issue, that we may need to study it further. And I also want to restate Mark's comment. The likelihood principle by the likelihood paradigm is that all the information you need is contained in likelihood function. So that's, we are truthfully reflecting or communicating the so-called statistical evidence contributed from each data pattern. And we have more question. Yeah, Fan said, the paper about the calibration in the Bayesian meta-analysis is a work in progress. So maybe Fan later can update the group about the status. And the next question is there a way from Liu Cong, is there a way we can identify outlier, meaning site with a systematic bias by analyzing those likelihood aggregately? That's a very interesting question. So when you say outliers, you mean the causal effect being very different from the causal effect from one particular study being very different from others, right? Is that what you're saying?
Or maybe some confoundings only existing on some some sites, which can be due to the EHR quality itself, or basically some healthcare process different from other sites. So in that case, I'm wondering, is there a way we, let's say, since we already have those aggregate likelihood data available from each site, maybe we can say, okay, some sites they are outliers, and before we actually aggregate all those likelihoods together, we may want to reconsider, put the name.
Yeah, I believe that was at least to some degree was handled by Mark's Bayesian meta-analysis framework, because my understanding, Mark, you can correct me. My understanding is that the current Bayesian meta-analysis framework is not assuming the causal effect follow a normal distribution. It's actually, you don't need to assume this exchangeability across different sites. So you could assume the causal effect to follow some multimodal distribution where you can account for some outliers among the sites, right? Is that the case? Or?
Yeah, that's absolutely correct, Yong. But I certainly don't want to take credit for Fan's great work here. This actually sort of raises the topic that I think in a community call in the next couple of months, perhaps we should talk about our Bayesian bias adjustment approaches and the fewer distributional assumptions that one needs to make if we move over to a Bayesian approach. Of course, there are also some disadvantages as well. So I think a balanced discussion of the advantages and disadvantages would be very helpful for the community.
But I think it's also important to realize that we still apply these study diagnostics on a per site basis. So even though the negative controls, as Yong was explaining, we combine those across sites and then apply empirical calibration, we still use the negative controls locally to decide whether or not that site is unblinded. And if a site is not unblinded, it does not participate in the meta-analysis. So it's not that we currently exclude sites because they're an outlier after passing diagnostics, but we do exclude sites just because they locally failed their diagnostics.
Well, Martin, I partially agree with you. Yeah, of course, it is important to examine them locally, right? And then basically before they merge into the aggregate analysis, we just get rid of them because they did not pass the local study diagnosis. But what I'm thinking here is, since we already aggregate them, right? So from a central point of view, you might also be able to basically get rid of them by comparing them with other networks, other sites, let's say likelihood functions. If they are very, very different, But I understand, you can assume there are multi-modes here, right? Then you are saying, okay, this is a distinguished sites when you want to put them into the meta-analysis. But I'm not sure, should we actually assume this kind of multi-model or actually simply remove them if there's only a few sites or just one sites, very different from other sites.
So my experience here is mostly anecdotal, but I must say, once you start applying these study diagnostics systematically, you don't actually see that many outliers anymore. I'm sure it could happen, of course, but that's been my observation until now. Like, if you systematically apply these diagnostics, then things start to behave much better than we've seen in the past.
Right. Of course, I agree.
Yeah.
All right.
I think, yeah, just one final comment. I think that's, that when you see outliers, that might be the time that we revisit this this pipeline. Whether we should the initial inclusion criteria for different study, should be revisited as well as this diagnosis criteria, right? So if we see lots of criteria outliers, that might be the time we revisit the formulation of the problem. So, but as Martijn said, that may not be the case in practice. So, okay.
Okay, yeah. Let me take over for the second part of the today's call. So Yong has gone over the theoretical background of what we're currently doing, synthesizing evidence across sites. I'm going to show you how it's done in practice, so the nuts and bolts. Just to give you a bit of an overview of technically what it currently looks like. So we have the study coordinator and several sites that are participating in the study, and of course, you have seen in prior calls that the study coordinator has designed the study and at the end has produced a JSON file that captures all of the design choices that were made, including the phenotypes that are used, but also settings for the comparative cohort design and the SCCS analysis and even prediction studies, etc. And so, of course, this JSON can now be distributed to any site that wants to participate in the study. Those sites have their data in the common data model, but they are also should have a strategist installation up and running. And currently, the mode by which we transmit this JSON file is through GitHub, although in the future there might be better mechanisms for doing this. Once sites agree to run a study, the JSON goes into strategist, it runs against the CDM, and after a while it produces a set of CSV files. That choice is deliberate because we found that these outputs need to be human reviewable. Sites want to know what they're sharing, and so CSV files seemed like a good choice for that. We then communicate those CSV files back to the study coordinator. Currently, we're using SFTP for that with a Odyssey SFTP server. The study coordinator then uses a package called the results model manager to upload those CSV files into a results database. We have contemplated whether like each site should be able to just upload directly to the results database, but just it's easier in terms of maintenance and making sure that everything fits together, that the study coordinator does that. And then once they're in this results database, which for these studies here are actually also in an Odyssey maintained Postgres database, we can then run a Shiny app on top of that. And that is something that I believe last time was already discussed, these Shiny apps and viewing all of the results. So that's basically where we are up to now. So now the question is, how do we combine across these sites? Well, again, we go through a process of designing the synthesis in this case. And I'll show you how that's done in a second. Again, this produces a JSON that goes into strategist. Strategist in this case doesn't run against the common data model anymore because it only needs these aggregate results, including the likelihood profiles that Yong mentioned. These are all already stored in the results database, so that will now be the input for Strategist. Strategist, again, will generate CSV files, which will go through the results model manager, also in the results database, and will then be viewable in the Shiny app. So both the original study and the synthesis are all done through Strategist, just in separate workflows, because of course one workflow is executed at the site and the other is executed by the study coordinator on the aggregate results only. So I'm just actually going to go through the R code for going through these steps, but if you want to follow along, you can go to the study package. I've added a evidence synthesis.r file that has all of the code that I'm about to show you. So as I mentioned, we first have to create this JSON file that specifies the meta-analysis. This probably will be pretty much the same for any future Odyssey study we do. So we first have to reference the evidence synthesis module, which has the settings functions. And basically, we have to define two things. One is the source of the estimates that we'll be synthesizing, and then the way in which we'll be synthesizing them. And we really just have two sources in this case. We've done a cohort method analysis and a self-controlled case series analysis. So those are two evidence synthesis sources. In both cases, we'll use the adaptive grid likelihood approximation that Yong mentioned. And in both cases, we'll use the Bayesian meta-analysis. So this is the Bayesian random effects meta-analysis with an alpha of 0.05. So here we're just defining the source, defining the meta-analysis, defining the source, defining the meta-analysis, then combining the two in a list and creating a module specification, and then combining, well, the only module that we have into a overall analysis specification. And so that's basically the JSON that is defining the analysis. And like I said, I would imagine that most Odyssey studies in the future will use this exact same code to do the meta-analysis. As you know, Strategist requires two things: the analysis specifications, which define what the analysis is, and then the execution settings, which basically defines, well, where do you find the database, where am I allowed to write locally, things like that. So we need to set up connection details. In this case, these will be connection details to the results server. So as you probably are aware, the recommended best practice is to not actually show credentials, for example, here in a Teams meeting, but use a use key ring to store those securely. So here we're just connecting to the database, getting the database schema where the results live. I need a local place where all the results can be written. I need to store the connection details with a specific key, and then I just combine all that into execution settings. And then the final step is to run Strategist, which basically has just two inputs: the analysis specifications and the execution settings. And that will run for a couple of minutes, and then you have results that you can upload to the database. I didn't include that code just because it's a little bit finicky, but it's all in that R file that I shared with you. Now, the nice thing, of course, once they're up there, you can then view them in the Shiny app. So I have uploaded them, and Jen has been so kind to actually activate the meta tab in the app. So we can now click on that, and we can actually see the results of the meta-analysis. So we have the various comparisons. I'm currently looking at the cohort method data. And so for the different targets, ranibizumab and aflibercept, I should be better at that. We can see what the results are for the end stage renal disease outcome. And so what you're seeing here, if we just look at the plot, is that we have here the three databases, and then we have the result of the Bayesian random effects meta-analysis. Obviously, it would be nicer if the meta-analysis was at the bottom and had a different color, but this tab is still a bit of work in progress. but it should matter to explain what's going on. One thing to realize is that, as Yong mentioned, there's quite a lot going on, going from the databases to the overall meta-analysis result, in that these are all calibrated estimates. So these per database estimates were calibrated using the estimates for the negative controls at each database, at each site. But then those negative controls, their estimates were meta-analyzed and then used to basically fit a new systematic error distribution, which was used to calibrate this overall summary estimate. So it sometimes can be a little bit hard to understand how the meta-analytic estimate was derived from the individual data sites. It's also important to realize that these databases, because they're shown here and actually shown with an effect, means they're unblinded, means they pass all local study diagnostics. And I think there are some examples later on where that is not the case. And so then they're automatically excluded from the analysis. So all of that is done automatically by strategists. So in this case, we see that none of the three databases produced a statistically significant effect. And if we combine across databases, actually, we have a pretty small point estimate with a pretty narrow confidence interval, suggesting that, well, there's not really much evidence of an effect. Obviously, it might be hard to look at the plot, so you can also just look at the table and actually see what the estimates are. So if we focus on the meta-analysis, this one, then I think these, yeah. So the point estimate is a hazard ratio of 0.95, going from 0.68 to 1.32. If we look at
more time.
Yep,
Harold asked a question in the chat that I think is relevant at this point to answer. So could you help to interpret that interval? And Harold's specific question, does it carry the semantics of a credible set or something different?
Well, so I definitely would argue it still is a credible interval in that the 95% of the probability mass is within those bounds. It is just incorporating different pieces of information, including, of course, the main estimates themselves, the random effect components that has been basically tried to extract from that, and then there is the uncertainty due to any systematic error that was observed from the negative controls. So it is still a credible interval. It is just summarizing way more information than people might be used to. If we go to another target, then here, and again, might be a little bit hard to see, but for aflibercept, we actually appear to have two comparators, comp1 and comp2, and it's hard to see here in this plot which one is which. You can see that in the table. So here it does actually say explicitly what the comparator is. We also see again here, if we look at the meta-analytic estimates, they're very close to one with tight confidence intervals. I believe if we go to the SOS plot, we don't actually see, we don't see anything. And the reason for that is that all sites, I think, failed all diagnostics, which wasn't entirely unexpected because of the nature of the exposures and outcomes. Yes. Anyway, that's all I had. Are there any questions other than one I already tried to answer?
Since we only have a couple minutes, please feel free to just unmute and ask a question if you have one. Here's a quick question. Let's have this sensitivity analysis over priors. Martijn or Yong or anybody?
You could do that, although the priors are not as strong, so I don't feel that we really need to play around with them too much.
Yeah, I wonder, Mark, do you have any comments on this, like the sensitivity to the prior? I know you are trying to make it as non-informative, as flexible as possible, right? So.
Yeah. I mean, there certainly are cases where one would want to use in informative priors. I think when we have a more extensive presentation on the kind of Bayesian approach that's simultaneously doing bias correction, or sort of an approximation to our calibration approach, that would be a great opportunity to look at sort of sensitivity to different prior choices and have a discussion of when putting informative priors in there are necessary. In this particular case, I mean, we are using a Bayesian procedure to fit the random effects models, but then we're using empirical calibration over those estimates. And empirical calibration is strictly a frequentist approach that tries to return nominal, in this case, coverage properties. So the final sensitivity to priors is going to get kind of washed away in trying to return to these nominal frequentist properties. Nonetheless, if you were to put really poor priors on there, you'd have a hard time returning to the nominal 95% coverage. In our experience, we haven't found that, but it certainly warrants much further exploration.